Welcome to the Deep Dive, where we cut through the noise to get you straight to the essential insights. Today, we're plunging into the exciting, but also incredibly complex world of securing AI agents. We've pulled together insights from a really fantastic talk by Jared Hansen. He's a pioneer in identity and access management for AI, and also, created the Passport.js framework, which is huge. Our goal today is to unpack this core challenge. How can we give AI agents the broad access they need to be, well, truly useful, without opening the door to massive security risks? We'll start with current practices, look at a real-world case study with a new protocol called MCP, and then explore the future, the cutting edge of agent security. And we'll do all this through the crucial lens of OAuth.
Yeah, it's a really fascinating dilemma, isn't it? We're all incredibly excited about the power of LLMs and these AI-powered agents. I mean, they're designed to automate tasks, make our lives easier. And the more connected, the more capable an agent is, the more useful it becomes, obviously. But here's the catch, right? Granting that broad access immediately introduces pretty significant security risks. You're faced with what feels like, well, an impossible choice. It's either grant wide access and accept the security issues that come with it, or limit their capabilities and sacrifice critical business value.
That really is the core tension. So when we talk about this in practice today, how are many of these agents typically set up? And what are the specific problems, the attack vectors, or even just the operational headaches that pop up when you try to scale that approach, like to hundreds or thousands of agents?
Well, the current common practice, which is frankly pretty problematic, is for many agents to rely on static API keys. These keys are usually long-lived, they're broadly scoped, and you basically just paste them directly into configuration files or maybe environment variables, and the agent just runs with those credentials. Now, when you start thinking about scaling this, imagine managing hundreds, maybe thousands of these static keys across a huge network of agents. It quickly becomes, well, an unmanageable security and operational nightmare. The attack surface just explodes, and trying to revoke or rotate those keys becomes this massive task.
Oh yeah, I can almost picture the spreadsheets trying to track all those keys. Definitely a real ops headache. But luckily, this isn't entirely new ground we're treading. We already have a powerful, pretty well-established way to move away from static secrets towards dynamic access. And that's where OAuth comes in, right?
Precisely. OAuth isn't just some buzzword, it's a really robust framework for delegated authorization, and it directly addresses these scaling issues we're talking about.
Okay, so many of you listening are probably familiar with OAuth already, maybe through things like signing with Google or connecting apps like Calendly to your Google Calendar API. But for our discussion today on AI agents, let's quickly recap its core function. You said it's a protocol that allows applications, which we call clients, to securely request access to APIs or resource servers. But the crucial part seems to be this mediating authorization server. Why is that mediation so critical for securing modern applications, and how does it specifically set the stage for these AI agent challenges?
Right. That mediation is the absolute game changer. Think of it like this. When Calendly wants to access your Google Calendar, it doesn't ask for your Google password. No way. Instead, it sends a request to Google's authorization server. That server, Google, checks you're logged in. It prompts you for consent, asking if Calendly can access specific things like viewing or editing your calendar. And if you say yes, then Google issues what's called an access token back to Calendly. Calendly uses that token to talk to your Google Calendar API. So essentially, Google is vouching for Calendly, telling your Calendar API, hey, this app has permission because the user agreed, but only for these specific actions. This fundamentally shifts the trust model away from sharing your actual password.
That makes the mechanics much clearer. And I've heard terms thrown around like refresh tokens and authorization code flows. How do those fit into this picture? Are they important here?
Yeah, they are. Refresh tokens are a really clever mechanism. They allow those access tokens we just talked about to be short-lived, maybe only valid for an hour, or even less. When an access token expires, the application can use the refresh token, which is longer-lived but more restricted, to get a new access token without bothering the user again. This rotation really enhances security. And the authorization code flow, that's the standard interaction you described with Calendly. It's a typical way a user delegates access, usually involving that browser pop-up or redirect where you see the consent screen. It's what most people interact with daily.
Okay, got it. Now, one area I find particularly interesting, and honestly, it's a common point of confusion, is how OAuth often gets used for identity. Sign in with Google, sign in with Facebook. Can you walk us through that? Because you said OAuth is fundamentally an authorization protocol, right? Authorizing access to something. How does it end up being used for logging someone in?
That's a great question, and it highlights a really clever repurposing of the protocol. When OAuth is used for sign-in, the API the application is asking to access isn't your calendar or your files. Instead, it's a special API, often called a user info endpoint, that simply returns claims or information about the logged-in user, things like their unique ID, maybe their name, email address. So while OAuth itself is still authorizing the application to access that user info API, the result of getting that information is that the application now knows who you are. It's not technically authenticating you directly, but it's proving your identity because a trusted third party, the authorization server, like Google, is vouching for you.
Oh, okay, so you're authorizing the app to get your identity info from Google. And this pattern became so common, it actually led to a whole separate standard, OpenID Connect or OIDC.
Exactly right. OIDC is essentially an identity layer built right on top of OAuth 2.0. It standardizes things like the format of that user info API response so applications know exactly what to expect. It also introduced some specific terminology like identity provider instead of just authorization server and relying party for the client application. But the core concepts are really the same. OADC also introduced something called the ID token. This is a cryptographically signed assertion, usually a JWT, that contains user information directly. It's kind of an optimization, so the application can verify the user's identity just by checking the signature on the ID token without having to make a separate call to the user info endpoint. It streamlines things.
Okay, that clarifies the OIDC connection. So zooming back out to core OAuth, we have these three key roles: the client, the app or agent, the resource server, the API, and this crucial mediating authorization server. What are the big picture benefits of having that distinct authorization server? What fundamental problem does it solve for these modern ecosystems of apps and APIs?
The primary benefit, really, is offloading all that complexity around authentication and user consent away from the resource servers, the APIs themselves. The APIs no longer have to worry about handling passwords, managing multi-factor authentication, implementing consent flows, tracking sessions, all that stuff. All that responsibility is securely centralized in the authorization server. Its job is just to authenticate the user, get consent, and issue tokens. Then, the resource server's only job becomes much simpler. Just validate the token it receives, make sure it's legit and hasn't expired. This model allows security policy to be centralized, which is huge for enterprises. It enables these vast, secure ecosystems of interconnected apps and APIs we use every day. And fundamentally, it separates concerns, which is just good, robust security architecture.
Right, that centralization seems key, taking a massive security burden off individual API developers.
Okay, so with this solid foundation in OAuth, the roles, the flows, the benefits, it sounds like, applying it to a new protocol, like this multi-party chat protocol, or MCP, should be fairly straightforward for securing AI agents. You'd think, okay, agents are clients, MCP servers are resource servers, get an OAuth server. Simple, right? But as we often find with cutting-edge tech, theory meets reality, and well, that's where things got really interesting with MCP and where a very public lesson was learned.
In theory, yes, it should have been simple. Just map the roles. Agents are OAuth clients, MCP servers are OAuth resource servers, and you need a separate OAuth authorization server. But MCP is, as you said, relatively young, maybe 7 months old at the time of this initial work. The very first version, which you could maybe call the OAuth version, actually had no authorization at all. It was mainly intended for local testing of MCP servers. But naturally, the discussion quickly turned to how to add proper, robust authorization for real-world use. And that discussion led to a first attempt at integrating OAuth directly into the MCP specification itself, which apparently didn't quite land correctly.
Yeah, far from it, actually. An early draft specification published around late March, it correctly identified MCP agents as needing to implement the client side of OAuth. That part was fine. But then it stated that the MCP servers should implement all of OAuth 2.0, including user authentication, consent flows, and token issuance. This was a really problematic design because it effectively collapsed those three distinct OAuth roles, client, resource server, and authorization server, into just two. It was asking the MCP server to be both the resource server, handling chat messages, and the authorization server, handling logins and issuing tokens.
Wow, okay. I can immediately see how that would muddy the waters and, well, probably raise some serious eyebrows in the identity and security community. And it sounds like it led to some very public, very immediate feedback.
Oh, absolutely. It was fast. Just 5 days after that draft spec was released, Christian Posta published a blog post titled, "The MCP Authorization Spec is a Mess for the Enterprise." It went viral pretty quickly, and it specifically called out that collapsed role issue and why it would be a disaster for enterprise adoption, forcing every MCP server vendor to build a full-blown OAuth server. Then Aaron Perkey, another really key figure in OAuth standards, followed up just days later with his post, "Let's fix OAuth and MCP." He pointed out how the diagrams in the spec were confusing because they showed the MCP server handling authorization directly. This kicked off extensive public discussions, including, I think, a pull request on the spec itself that got hundreds of comments. Everyone was basically pushing back, saying, no, you need to separate these roles. This isn't how OAuth works best. It was a really rapid, very public course correction driven by the community's insistence on sound architectural principles.
And wasn't there a bit of irony here? Didn't Jared Hansen himself, whose talk we're drawing from, actually suggest the correct model earlier on?
Yes, that's right. He had apparently recommended early on, before this problematic draft, that MCP servers should just be modeled as standard OAuth resource servers, which is exactly what the community ended up demanding.
That's fascinating. What does that tell us about, the life cycle of developing new protocols? Especially when security architects are trying to influence those initial designs, is there maybe a common resistance sometimes to adding what seems like complexity early on?
Oh, absolutely. It's a classic tension, isn't it? You're trying to get something functional out the door quickly, get the core thing working, in this case, getting chat messages to flow. And sometimes authorization or robust security architecture can feel like an afterthought or like an extra layer of complexity you don't need for V1. So Jared's initial recommendation to use a separate auth server might have seemed like, oh, that's another component we have to stand up or integrate with early on. But the public outcry later really proved that neglecting those fundamental architectural principles, even in a brand new protocol, inevitably leads to significant rework, confusion, and, well, public criticism down the line. It's a powerful reminder to bake security and good architecture in from the start, not try to bolt it on later.
A lesson learned in the public square, it seems. So what was the positive outcome of all this intense feedback for the MCP specification? Did they fix it?
Yes, the great news is they did. The subsequent draft of the MCP specification fully incorporated this feedback. It now cleanly models the OAuth roles, clearly separating the OAuth server as a distinct external entity. This massively simplifies the job for anyone building an MCP server. Now, they only need to worry about being a good resource server validating the OAuth tokens that come in with requests, usually over HTTP. All the really complex parts, user authentication, MFA, consent, token issuance, that's all correctly offloaded to the dedicated OAuth authorization server. So yeah, we're back to a pretty good, sensible place for authorizing connections between MCP clients and MCP servers using standard OAuth patterns.
Okay, that's a significant improvement and a good outcome for the current state of MCP. But if we're really talking about the future of securing AI and these complex agent interactions, fixing this one specific protocol connection, while crucial, feels like it's just scratching the surface, doesn't it? This is where the complexity seems to really ramp up.
Exactly. We've mostly talked about user delegation using OAuth's authorization code flow. That's what applies well to the MCP scenario where a user is initiating the connection. But what about agents that need to communicate with other agents? Or maybe agents needing to call other APIs or even other MCP servers, but doing it on their own behalf, not necessarily acting directly for a user at that moment. That scenario requires understanding a different part of OAuth, specifically the client credentials flow. This is where the agent itself is the principal, the entity seeking access, not a human user delegating access to it.
Right, and if we're going to have potentially hundreds, thousands, maybe even millions of these autonomous agents interacting, the whole question of agent identity becomes this enormous challenge. I mean, the current friction of manual client registration, going to a developer portal, getting a client ID in secret, pasting that into config files that just won't scale at the speed AI agents seem to be multiplying. What are the emerging solutions here? How do we authenticate these agents reliably at massive scales?
Yeah, it's a critical bottleneck. There actually is an existing specification called dynamic client registration, which theoretically allows agents to request their own credentials at runtime. But the truth is, it hasn't seen much meaningful adoption in over a decade. Why? Because the registration request itself is typically uncredentialed. The agent just shows up asking for credentials. This makes the agents effectively anonymous at the point of registration, which makes them really hard to trust. It's not a viable way to build trust at scale. Now, for public clients agents where you don't necessarily need rigorous identity verification, maybe like a simple informational bot, there's an emerging spec called push client registration. This introduces a concept using a well-known string that allows an agent to quickly register itself, basically skipping the manual portal step and reducing the need for the auth server to score state for every single one.
Okay, that sounds like it could simplify things for certain types of agents, the less sensitive ones. But for authenticated clients, where trust is absolutely paramount, like an agent handling financial data or accessing private APIs, how do you handle identity at that scale without drowning in manual registration?
Right. For those authenticated clients, the proposal and where the thinking is heading is to leverage existing robust infrastructure, specifically using URLs like agent.example.com as the client identity within OAuth flows. The agent would then cryptographically authenticate itself. It could do this by signing specific requests or assertions using a private key, and the authorization server could verify that signature using the corresponding public key, perhaps discovered via DNS or another mechanism linked to that URL. This essentially integrates agent identity into the existing public key infrastructure, PKI, we already use for websites, making it potentially very scalable and verifiable without needing manual steps for each agent instance.
That makes a lot of sense, leveraging strong cryptography tied to a verifiable identifier like a URL. Now, beyond just knowing who the agent is, there's also this growing concern about agent attestation. What does that actually involve, and why is it becoming so important, especially in a world where agents might be processing sensitive data and then sending it off to LLMs?
Agent attestation tackles a really critical trust gap in the chain. Okay, so an agent connects to your resources, maybe reads some sensitive data, fine. But then it often needs to send that information to a large language model, maybe hosted by a third party, for processing or to generate a response. As users or organizations, we need some awareness and ideally control over where our sensitive data ultimately winds up. Is it going to a trusted, known LLM or somewhere else? Now, in highly controlled environments, you could maybe treat the LLM as just another internal API and manage access that way. But that's pretty limited. When agents are deployed on user desktops or mobile devices or other environments where you don't fully control the software stack, attestation becomes really vital.
So how do we actually get that level of assurance? How can we know what the agent software is and what it's doing before we let it handle sensitive data or talk to external services?
Well, there's significant work happening right now, particularly within the IETF, the Internet Engineering Task Force, on things like remote attestation and supply chain security. The idea is to allow systems to cryptographically attest to the precise state of a device, the hardware, the operating system, and the specific software like the agent application running on it. This attestation could prove, for example, that the agent hasn't been tampered with and that it's configured to only send data to specific approved LLM endpoints. The goal is then to integrate this attestation information directly into the OAuth authorization flows. So the authorization server wouldn't just check who the agent is, but also what it is and whether its current state is trustworthy before issuing tokens. It adds another crucial layer of assurance.
Wow, that's a huge step towards building real trust in these systems. Okay, let's shift gears slightly. There's also transactional authorization. Oath scopes, like read calendar versus write calendar, are a big improvement over just passwords. But for agents, especially ones doing complex tasks, even those scopes can feel too broad, too coarse-grained, and often too long-lived for really dynamic, high-stakes interactions. Is that fair?
Oh, precisely. Think about an agent involved in financial transactions or commercial activities. We can't just grant it a scope like write access to a bank account and let it run wild. That's terrifying. We'll need much finer grained control. We'll need to authorize things on potentially a transaction by transaction basis. Imagine authorizing an agent to perform a specific action, like debit up to $500 from account X, but only for purchasing approved supplies, and this authorization is valid only for the single transaction attempt. It's about moving away from these broad, persistent permissions towards highly dynamic, context-aware authorizations that are specific to the task at hand. There's a specification being explored called Rich Authorization Requests, or RAR, that aims to address this. It allows the client, the agent, to send much richer context about the specific operation it wants to perform when it requests authorization, enabling the authorization server to make much more granular decisions.
That sounds essential for any kind of automated commerce or financial interaction. It feels like we need security not just at the initial connection, but really woven throughout the entire workflow, especially when agents are part of complex, multi-step processes involving other services. Which brings us neatly to the idea of chain of custody. You mentioned MCP only covers that first leg, the agent connecting to the MCP server. But what happens after that? What if the MCP server needs to call another internal API on the user's behalf? Or what if agents need to call other agents, maybe across different domains or running on different servers entirely? How do we track and authorize that?
Yeah, that's the critical next step, and honestly, it's where the real complexity, but also the real power of agent ecosystems emerges. For those internal API calls, like the MCP server needing to call, say, a user profile API within the same organization, there's a technique called OAuth token exchange. It allows a service that received a token, like the MCP server, to exchange it for a new token that's valid for a different internal service, still acting on behalf of the original user or agent. But for cross-domain authorization, imagine an agent on server A needing to trigger an action via an agent on server B belonging to a different company that's harder. We're looking at concepts like identity chaining across domains and standards like the identity assertion grant. These essentially allow tokens or signed assertions to carry identity and authorization information across different trust boundaries, perhaps between different companies' authorization servers. The ultimate vision here is to achieve end-to-end visibility. We need a verifiable chain of custody for authorization flows as they traverse these potentially complex graphs of interacting agents and services. Every step needs to be properly authorized and, ideally, auditable.
End-to-end visibility across complex graphs. That sounds challenging but necessary. And the complexity doesn't stop there, does it? Because OAuth, traditionally, often assumes a user is actively present, usually sitting in front of a browser ready to click Allow on a consent screen. But agents often work autonomously in the background. Users might step away from their devices for hours or days. So async interaction seems like another major frontier for authorization. How can an agent request more access if it suddenly needs it for a task, but the user isn't right there in a browser? Can it use things like SMS or push notifications?
That's a fundamental shift from the classic browser-based OAuth of flows, you're right. The challenge is enabling secure, real-time, potentially out-of-band communication for getting user consent or authorization decisions. Imagine an agent running a long task overnight. It hits a point where it needs permission to access a new resource, or maybe it needs approval for a transaction that exceeds its pre-authorized budget. Instead of just failing, the ideal scenario might be for the agent to trigger an authenticated push notification to the user's registered phone. The notification would clearly explain what's needed and offer simple approve or deny buttons. Making this work securely requires rethinking how user interaction, consent prompts, and cryptographic verification are woven into the OAuth flow for these asynchronous, non-browser-based agent operations. It's an active area of exploration.
Definitely tricky. And finally, looking even further ahead, as AI interactions move beyond just text, we're starting to see agents communicate with us via voice, maybe video, or operating entirely in the background based on sensor data or other triggers. Surely new security considerations must be emerging there too. How do we secure those interactions when they become less about a click in a browser and more about a spoken command or a continuous stream of video data?
This is truly the frontier, where AI interaction meets real-time communication security. The good news is we're not starting entirely from scratch. There's a lot of valuable prior art in the communities that built the standards for real-time communications. Think about protocols like SIP, which powers voice over IP, XMEP, used for instant messaging, and WebRTC, which enables real-time audio and video directly in browsers. Those communities have already tackled many challenges related to securing real-time, often ephemeral, data streams, dealing with things like endpoint authentication, media encryption, and preventing eavesdropping or tampering. We can absolutely leverage that existing knowledge and adapt those principles to figure out how we secure voice commands to agents, how we ensure the privacy and integrity of video feeds used by AI, and generally how we build trust into these newer, more dynamic interaction modalities.
Wow, what a journey. We've really covered a lot of ground today. We started with that fundamental dilemma of agent security usability versus risk and got a solid handle on OAuth's core principles. Then we saw how those principles were applied, debated, and ultimately refined in the real-world case of the multi-party chat protocol. And finally, we explored the really complex but absolutely vital future needs for truly securing AI agents, everything from dynamic identity and attestation to transactional authorization, chain of custody, async interactions, and even voice-video security.
Absolutely. And addressing these challenges, it's not just, an academic exercise or something for standards bodies to worry about. It's really essential if we want to achieve a future where AI is both incredibly powerful and beneficial, but also safe and secure. We need systems we can trust, especially as agents become more autonomous.
That's the goal. So let's leave our listeners with this thought. As AI agents become ever more integrated into our daily lives, truly transforming how we work, how we interact, maybe even how we live, what kind of systems we need to secure next?